In this video, I'm just going to give a brief introduction of stoichiometry. And stoichiometry is very important in chemistry or in chemical engineering because it gives us answers to the questions like how much of the reactants are required. Let us say you are a chemical engineer at a plant. You want to know how much of the reactants, which are raw materials, by the way, that you require maybe in a month or in a week. And after the month or during the reaction, you may also want to calculate how much of the reactants were used. Stoichiometry also gives you the answer to the question, how much of the products were produced. You want to know how much product were produced, or even to predict how much product will be produced. Let us say you are starting a new project and you have the information about how the reaction goes, and then from that you can predict the amount of products that you expect at the end of the production period. You may also want to know the amount of flue gases released or that are going to be released, and even to know the impurities in products, the amount of the impurities in products. So stoichiometry is a very important subject. Most of the calculations that chemical engineers do, or even chemists do, are part of stoichiometry. It involves material balances. It involves understanding the law of conservation of mass and the law of conservation of energy, which you use to do things like energy balances. So in this video, I'm just going to give a brief introduction of stoichiometry. I'm not going to cover everything, but I'm just going to give a brief introduction of the important aspects that you need to know, or that people who are studying elementary chemical engineering or elementary chemistry should know. So let us start. I'm going to start here with a reaction, an ordinary reaction that is occurring by writing the chemical equation of that reaction. So let us assume we're just talking about an ordinary combustion reaction. These are very common reactions, so I'm going to use this. It is a combustion reaction. So we know that fuels combust or fuels burn, and that reaction is called a combustion reaction. Let us assume our fuel here is ethanol. Our fuel is ethanol, which is C2H5OH. This is our fuel, ethanol. And when we say it is a combustion reaction, we mean that we are adding oxygen to the fuel. So this is C2H5OH. It's combustion, so we add oxygen, O2. The products of this reaction is carbon dioxide, CO2, and water, H2O. What we have here is a chemical equation. It is representing the chemical reaction of ethanol and oxygen. This is what we have. But we know that chemical equations obey the law of conservation of mass, or the law of conservation of matter. The amount of the mass of the reactants will equal to the mass of the products at the end of this reaction, because mass is not created or destroyed during a chemical reaction. It also has to obey, because it is an ordinary chemical reaction, it also has to obey the law of conservation of atoms. In other words, I mean that if we had two carbon atoms entering into our reactor, at the end of the reaction, we should still have two carbon atoms, because during a chemical reaction, atoms are not destroyed and no new atoms are created. There's just a rearrangement of atoms in here. To illustrate or to show that we understand that mass is conserved, we have to balance the equation. So we have to balance the equation. So balancing equations, chemical equations, balancing. Balancing chemical equation is actually a way of saying I know that atoms are not destroyed or no atoms are created during a chemical reaction. It is also a way of saying you understand the law of conservation of mass. So we are going to balance this equation. If you have forgotten how to balance chemical equation, you can check the video that I did on balancing of chemical equations. If you have forgotten, we balance the element last. In this case, oxygen is an element. We balance it last. Let us start by balancing carbon. I'm going to use a green pen for that. When you're balancing a chemical reaction, you're just changing the numbers behind these chemical formulae. So we are not changing the formulae themselves. We're just changing the numbers behind, which I will call coefficients. I'll explain what they're called. So this is 2 carbon atoms to the left-hand side. To the right-hand side, we have 1. So we multiply here by 2. Then let us go to hydrogen. We have 6 hydrogen atoms to the left-hand side. To the right-hand side, we have 3. If we multiply here by 3, we have 2. If we multiply by 3, we have 6. So let us multiply here by 3. Then let us balance the oxygen last. We go to the side with the more oxygen atoms. To the right hand side, we have 3 plus 4, which means we have 7 oxygen atoms. To the right hand side, we have 7 oxygen atoms, and to the right hand side, we have 3, which means if we multiply here by 3, we now have 7 to the left hand side, 6 here plus this 1 on ethanol. We now have 7 oxygen atoms. So we have balanced. This is what we call, this is now a balanced chemical equation for the combustion of ethanol. Now, what we have behind this, let me wrap this out. These numbers that we have, that I wrote in green, these numbers here, okay, so these numbers that I wrote in green, we call them stoichiometric coefficients. Those are called stoichiometric coefficients. So these 3 here, and these 2 here, and these 3 here. Behind the ethanol, there is 1. Obviously, we don't write the 1, but it is there. And let me write it. So we have a 1 here, even though we didn't write it. We call these stoichiometric coefficients. These are stoichiometric coefficients. Balancing a chemical equation is the first step that you take when you are going to do your stoichiometry, or when you're going to answer questions like how much of the reactants was used, or how much of the products was produced, or how much of impurities do we have in our products, or how much of the flue gases are going to be released. All these questions, you can answer them if you have balanced your equation, because these stoichiometric coefficients have got a very important meaning. Now, from here, I want to go to how you interpret so the interpretation, I'm going to call that the interpretation of chemical reactions. What does it mean? Interpretation, okay, of chemical equations. This is very important. If you are a student of chemistry, or maybe chemical engineering, or anything of the sort, you should know how to interpret a chemical equation. If I write a chemical equation, you should know what it means. So let me write that chemical equation we had. It is saying C2H5OH, which is our ethanol. It's reacting with 3O2 Okay, the products here, we said we had 2 CO2 plus 3 H2O. This is what we had. Okay, let me write this because I want to add something. 3 H2O. Good. If we look at what we have here, this is a balanced chemical equation. So someone will come and say, so what does it mean? What are these numbers telling us? What are these numbers telling you? As they are, or as they stand now, they tell you this. This is what it's telling you. They tell you the ratios. See? Okay. The mole. They tell you the mole ratios of reactants and products. Reactants and products. This is what we get from this equation. In other words, I said mole ratios. Moles, which shows you the quantity. A mole is a measure of the quantity of material. So what if we were to interpret this reaction? We're going to say 1 mole of ethanol reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. This is what they tell us. Sometimes you see to this equation, they may write something here. They may write something like, maybe before, after ethanol, they write something like maybe L. And on oxygen, they write something like a G. On carbon dioxide, they write a G. And on water, they also write, let's say, a G. What they're saying here is during this reaction, the L, the G, and these G's that we have here, we call these state symbols. They're simply telling you the state of they're telling you the state of the reactant, what it was. So L is for liquid, G is for gas, sometimes it's S for solid. So sometimes you see a subscript S to say it was a solid. So they're telling you the state of those reactants. But the numbers behind these numbers here, they tell you the mole ratios. They represent the number of moles. If your reactants and products are gases, I want to say this. So these mole ratios apply. These apply to all reactions. To all reactions. This is very important because when you're doing your stoichiometric calculations, you need to understand that, can I interpret my equation in terms of moles? Yes, any chemical equation can be interpreted in terms of moles using these stoichiometric coefficients. As I did here, I said 1 mole of ethanol is reacting with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. This is what it is saying. However, if these reactants here and products are in gaseous form, okay, or in gaseous state, okay, in gaseous state, this only applies in gaseous state. I mean, if the products and the reactants, all of them are gases, if it is like that, these the stoichiometric coefficients also represent volume ratios, okay? Coefficients also represent volume ratios. This is very important. It actually makes your life easier if you can spot it. Let me remove this L here. for ethanol, and I'll put a G. In other words, I'm going to say, oh, my ethanol is in gaseous form. See, now my ethanol is a gas. I'm reacting it with oxygen, which is a gas, to produce carbon dioxide, a gas, and the water that is produced in gaseous form. If I have this, I can also say 1 volume of ethanol reacts with 3 volumes of oxygen to produce 2 volumes of carbon dioxide and 3 volumes of water. In other words, I can say 1 cubic meter if my volume is in cubic meters, or even 1 liter if I want to use liters. I can say 1 liter of ethanol reacts with 3 liters of oxygen to produce 2 liters of carbon dioxide and 3 liters of water. If our reactants and our products are in gaseous form, we can read this in terms of volume. However, if they are not all in gaseous form, you can only read them in terms of moles. So this gives you an idea of how you do your stoichiometric calculations. So I'm now going to go to explain what you do, or how you approach stoichiometric calculations, especially if your reactants and your products are not in gaseous form. I'm going to focus on that. If your reactants and your products are not in gaseous form, how do you approach? It's a general approach, but you just need to know this. It's a general approach, but you just need to know this. So let me introduce here. All right. Steps in stoichiometric calculations. Steps in stoichiometric calculations. I'm just giving you here general knowledge that you should know, so that when you're doing your stoichiometric calculations, you know what to do. So first, you need to write the chemical equation. Write chemical equation. Okay, write chemical equation and balance it. This is a very essential step, because most of the time we give you a equation that is a weight equation without any chemical equation attached to it. It's now your job to write the chemical equation and then you balance it. This is a very important step. In fact, if you don't do this step right, there is no way you're going to get your stoichiometric calculations correctly. So do this properly. Write your chemical equation and then you balance the chemical equation. And after that, calculate the mole ratios. Calculate or determine the mole ratios. The mole ratios are there on your chemical equation. You're going to just look at the stoichiometric coefficients. They tell you the mole ratio that, oh, 1 mole of this requires how many moles of that, or 2 moles of this requires how many moles of that. You get that from using the so determine or calculate your mole ratios, or sometimes volume ratios. If they are gases, you can be talking of volume ratios. So let me say mole or volume ratios. Mole or volume ratios. If you're having gases, that's where you should think of volume ratios. You determine these, and then now, if you have your reactants or products in mass, if you have your reactants and products given in kilograms or other mass units, convert them also to moles. So convert all masses to moles. If you're given, let's say they told you that we have 2 kilograms of ethanol, that is not very useful in your stoichiometric calculation, that we have 2 kilograms of ethanol. It's not very useful. What is useful is how many moles of ethanol do we have. So we may just need to convert that mass of ethanol into moles of ethanol. That's what we should do. Convert into moles, and then the last thing that once you do this, now you can now do the stoichiometric calculations. Now from here you can do the stoichiometric calculations now. Stoichiometric calculations. These are my steps that I use, and I'm going to show you how, when I'm using these steps, I'm going to use them in this question, how you use all these steps. So you write your chemical equation, you balance it, then after balancing it, you determine the mole and volume ratios, then you convert all the masses that you're given to moles. And then once you do that, you can do the stoichiometric calculations straightforward using simple proportion. So now let me go to putting this in practice. I want to say in this video, I'm going to do the calculations relying on this approach. However, there is another approach that we call the first principles approach in these calculations. I'm going to do another video where I explain the stoichiometric calculations using first principles. It is quite a very good method, and I'll show you how you do that. But for now, let us rely on this and see what we can do. Now I'm going to use my example once more. So I'm going to use the example of, yes, we said we have, so how, no, let me not say how, let me say calculate the mass of CO2, carbon dioxide, produced calculate the mass of carbon dioxide produced. Okay, let me write it here. Produced when 2 kgs to let me say 2 kgs of ethanol is burned completely. I don't know, let us say we're going to be given us 6 marks for this. We want to know the amount or the mass, because the mass of carbon dioxide that is going to be produced when 2 kgs of ethanol is burned completely. We want to know it for some reason, because these days we're talking of global warming, and carbon dioxide is one of the greenhouse gases. It contributes to global warming. So you might be interested in knowing how much of it is produced every time you are burning your ethanol. So you want to know that for whatever reason. Now, this is the approach. I'm going to use the steps that I gave you. I said the first step is to write. So one, I'm going to write the chemical equation and I'll balance it. So this is ethanol. It's C2H5 or H plus O2. No one tells me that I'm adding O2, but we know that when it's burning, we cannot do burning without oxygen. If there is no oxygen, there can be no fire. We know that. So oxygen is responsible for combustion. So we have to add oxygen. That is what it means. And then the products of this, if it's complete combustion, this word here, complete, is not there, is not idle. It is telling you that this combustion is going to produce carbon dioxide and water, because if it is not complete, it produces carbon monoxide. So we got CO2 plus H2O. Then I do the balancing. I said I put a 2 here. I put a 3 here. Then this is a 3. Now it is balanced. So I have done the first step of writing my chemical equation and balancing it. If there are marks, I'll get some marks for doing this. So maybe let us say I'm getting 2 marks for doing this. Whatever, let's say 2 marks. And then from here, I go to the mole ratios are here. So what do I know? I know that these are the mole ratios. So I'm going to talk of the mole ratios. So it's 1 mole, C2H5 or H2, 2 moles CO2. This is a very simple thing. Now, I'm getting this from my balanced chemical equation, that if I have 1 mole of ethanol and I burn it, I'm going to produce 2 moles of carbon dioxide. This is what I should get. Now, we need to now convert these moles to mass. We need to look for what is called the molar mass. The mass of 1 mole, we call it the molar mass. So the molar mass here, molar mass, molar mass. We are going to rely on a periodic table. So for ethanol, it is C2. So for ethanol, it is C2H5 or H, and you need to know the masses of each element in the formula. So you need to know the molar mass of each element in the formula. So carbon, it is 12. So we have 12 times 2 plus, so it's 12 times 2 because we have 2 carbons here, plus hydrogen is 1 and we have 6 of them, so it's 6 times 1, and oxygen, or the oxygen atom, it is 16. So we are adding here plus 16 plus 16. Now this gives us the molar mass of C2H5 as 46. So this is 46. So that's 46 for ethanol. So this is 46. It means 46 grams per mole. And then for carbon dioxide, the molar mass is 12 plus 16 times 2. So that is 44. So this one, the molar mass is 44 grams per mole. That's the molar mass. Now, if we want to know the number of moles of, now I'm doing the 3rd step now, the step where we are converting masses to moles. We are given 2 kgs of ethanol. If we want to know the number of moles, N of ethanol, N represents the number of moles of ethanol. It is the mass of ethanol. Since our molar mass are in grams per mole, we're just going to use also grams per grams here. So let us convert this to grams. This is 2000 grams. We are dividing it by 46. We want to know the number of moles of ethanol that we have. So that is 2000 divided by 46 divided by 46. We get 43.478 moles of ethanol. Now we go back now to our ratio. We know that 1 mole of ethanol, if it is burned, it produces 2 moles of carbon dioxide. So there is a ratio of 1 to 2. Whatever number of moles of ethanol that you burn, you produce times 2 that for carbon dioxide. Now I'm going to finish this question now. So from here we can calculate the number of moles of carbon dioxide produced by simply multiplying this by 2. From the mole ratios, we can simply multiply this by 2, then we can know the number of moles of carbon dioxide produced. Let us go there. I want to put this off. Then we come here. We know that. So mole ratios I'm just going to interpret this. 1 mole ethanol, C2H5OH, produces 2 moles of CO2. We got this from our balanced chemical equation. Now we have 43. Now we want to know 43.478 moles of C2H5OH. We want to know how much it produces of carbon dioxide. This is what the question was asking about. They want to know how much of this produces. From our mole ratios, we know that it's 1 to 2. So whatever number of this that we have, it will be times 2 that here. Let us call this X. X will be 2 times this. Therefore, let us do the calculation. Let us finish our calculation. Therefore, moles of CO2 produced is equal to 2 times 43.478. 43.478. We find our final answer here in moles. So 2 times 43.478, we get 86.956 moles CO2. So this is the amount of carbon dioxide produced in moles. But remember, guys, that our question was saying how we wanted the mass of carbon dioxide produced. These are moles, they are not mass. You see, this is another important thing that you need to know when you're doing your stoichiometric calculations, that in most cases, most of the calculations are going to be done in moles. Then, so if you have masses, you convert them to moles. After you have your amounts in moles, you now convert them back to masses. What do we know? We know that number of moles is a mass over molar mass. So it means mass is equal to N times molar mass. Call it M. So it's N times the molar mass. N being the number of moles and M being the molar mass. And the number of moles of carbon dioxide that we have here is 86.956. We are multiplying this by the molar mass. Let me check my formula first. Maybe I'm using the wrong formula. We said N is equal to mass over molar mass, right? And N is equal to M over M. So this is mass over molar mass. That is the number of moles. Yes. Now, if we want M, we multiply this by N. Okay, good. It makes sense. So now we want to know the number of moles. So we multiply this by the molar mass of carbon dioxide, which we said it is 44. So multiply here by 44. Let's write our final answer, which is the answer that we wanted to know. 86.956 times 44, we get 3,826.064 grams. These are grams here that we have, which means we essentially, our answer is, the final answer that we're looking for is 3.826 kgs. So our answer is 3.826 kilograms of carbon dioxide. This is the amount of carbon dioxide produced when we burn 2 kilograms of ethanol. Very, very important calculations, especially in these days of climate change and global warming. We want to know how much of carbon dioxide that our fuels are emitting into the atmosphere. So this is a very important calculation. That's why I said stoichiometry is a very important subject in chemistry and chemical engineering, and even in environmental engineering and other disciplines. So this is how you do it. I have just done this one example, but I think it is enough to illustrate the steps that you take when you're doing stoichiometric calculations. I'm going to do another video using first principles, the same examples but done in first principles. Otherwise, thank you for watching the video. If you have any questions or any queries, just write in the comment section. Otherwise, give a thumbs up to the video, subscribe to the channel, and share the video with your friends. Thank you.